So how many of you guys have taken the exam already?
I did.
You did? How was it?
Yeah. I mean, I could have done better.
You could have done better?
Yeah.
Okay, so I have to take a look. So was it good to have your score? You pretty much graded everything. I think there's one thing I have to grade, and I'll have to look over it. Did all the images show up for you?
Yeah.
Okay. I had trouble with getting them uploaded, so. Okay. Okay, so I believe we did this last time, didn't we? Or do you guys want to do a recap real quick?
Recap real quick.
Recap.
Okay.
Recap.
Okay, so we're working on empirical formulas, right? So, and you guys remember what the definition is of an empirical formula? Anyone?
It represents the lowest integral ratio of atoms, the elements in a compound.
That's true, exactly. So we basically want to get the lowest possible numbers that aren't divisible by each other in terms of the ratio of the elements in that compound. So that would be the empirical formula. Now the empirical formula can be used to calculate the molecular formula. Sometimes we'll do analysis and we'll end up with the empirical formula, and then we'll have to work back to find out what the molecular formula is. And I'll show you a question like that a little bit later, okay? So, but for this one, so what do we know? So I'm gonna read the question, and I want you to think about it and figure out how we're gonna go about this process of solving this. So we have nicotine is 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. What is its empirical formula? So what do we know?
That we know the percentages that we have of each element.
So we know the percentage of what we have for each element. And we know that nicotine is made up of those elements, right?
Yes.
Is that true? So can I make an assumption? Can I say that if I have 100 grams of nicotine, how much of it is going to be carbon?
74.1%.
Okay, so then that's how many grams is going to be carbon? If I have 100 grams of nicotine.
74.1 grams.
Okay. How much of it is going to be hydrogen?
8.64 grams.
How much of it is going to be nitrogen?
17.3 grams.
Okay. So when we're comparing those ratios, we're comparing the moles because we know that moles are quantity. So we have grams. Are grams and moles the same thing?
No.
So how can I convert my grams into moles?
By using dimensional analysis.
Okay. How? What am I going to need?
So you need to put 74.1 grams and then
Do you use the mass of the element?
I'm going to need the mass of the element. And how much does that element weigh per mole?
12 grams.
12. Okay. So I'm going to use the periodic table to get the mass of the element. So it's 12 grams per 1 mole. Okay. And so then that's going to give me my moles. Anybody did the math? Just quick with the calculator.
6.18 mole carbon.
Moles of carbon. Okay.
Then over 1.24 mole.
Okay, can you repeat that, please?
Or are we doing the same question from last week?
Yeah.
Right?
Yeah.
Okay.
So this
So-
remains the same, correct? 8.64.
That's right, because we know that this is 1 gram per 1 mole. And then nitrogen,
14.
14 grams per 1 mole. Okay, so what do you guys get?
1.23.
Okay, so the next part is, what do we want to do?
Find the lowest.
Do you divide them by the lowest?
Divided by the lowest. 1.23 is our lowest. Okay. So what do you get?
5.
5.2. 5.02.
Well, we're going to round up to 5. We know it has to be a whole integer.
Oh,
And then here,
7.
and then nitrogen will be 1.
Mhm.
Okay, so then our empirical formula is going to be C5, H7, N. Piece of cake?
Yeah. Thank you for going over it.
Okay, so then if we want to calculate the molecular formula, if we have the empirical formula, so we've already determined our empirical formula, calculate the molecular formula, there's going to have to be another piece of information given to you. Often they're going to give you the molar mass of a compound for that molecular formula, or they're going to give you a range which it falls into. Okay, so if that happens, then all you're going to do is take the empirical formula and you're going to calculate its molar mass, and then you're going to divide the molar mass of the compound by the empirical formula. And then that's going to give you an integer to multiply by. I know that makes no sense until you actually see what I'm talking about. So let's give you an example. Okay. A compound with the empirical formula C2H5 has a molar mass of 58.12 grams per mole. Find the molecular formula of the compound. So what am I going to do?
Do you have to find the mass and the density?
Can you repeat that one more time? Do I have to find the mass of?
Do we have to find the volume equals mass divided by density, or?
Why would I do mass by density? So am I trying to convert it to liters? Or, so not density, that's not quite what I'm looking for. Yeah, I'm glad you remembered that, but think about what you're trying to do. In this case, you have the empirical formula. We have the empirical formula, and we have the molar mass of the molecular formula. So this is the molecular formula. It's the molar mass of the molecular formula. Okay, this is our empirical formula. So the first thing that we want to do, and thank you for stepping out, Thalia, but we'll try to get you straightened out here real quick in terms of what we're going to do. In this case, we want to find the molar mass of the empirical formula. How would I find the molar mass of the empirical formula?
Would you multiply instead of dividing? Like towards the end, how you divide it by the smallest number, would you multiply now?
No, not quite. So let me ask the question a different way. How can I calculate the mass of this compound here? 'Cause that
Using
would be the molar mass of that compound.
of the elements.
So I'll work with the elements. So how many carbons do I have?
2.
Two.
So I know that C2 has 2 carbons. I mean, C2H5 has 2 carbons. So it's 2. And then how much does each of those carbons weigh?
12.
Okay. So they weigh 12 grams per mole, right? So, and then I have 5 hydrogens. And how much does that weigh?
5.
1.
Okay. So we add this together. What is that? 24 plus 5?
29.
And that would give me my molar mass. Okay, so
Oh, okay, I get it.
Okay.
Yeah.
so that gives me my molar mass. Now I have the molar mass of the empirical formula, and I have the molar mass of the molecular formula. So if I have molar mass of molecular, formula over the molar mass of the empirical formula. Okay, so we have molar mass of the molecular formula is 58.12 grams per mole, divided by 29 grams per mole.
2.
Okay, so that gives me the factor that I need to multiply my empirical formula by. So literally, I have C2 times 2 and H5 times 2. So then that's going to give me C4 H10. And so this would be my molecular formula.
Okay.
Okay. How's it going?
Good. I just needed you to show me once.
What was that?
I need you to show me once because you have to like go backwards.
You're gonna have to go backwards.
Like go like, you know, find it the other way instead of the way you just showed us.
So if I wanted to calculate the empirical formula of this, we know we divide it by something that they both could be divided by and give me a whole number. That's 2. That just gives me the original what we had. So in this way, we just kind of we're working from the empirical formula to get to the molecular formula. Are you with me?
Yep.
Okay, so now let's do a hard problem, right? This is too easy. Want something more challenging, right?
Okay.
You all are supposed to say, yeah, we're ready, right? Let's be ready. Come on. But you guys like a challenge. I know it's in your blood. Okay, a 5.31 gram sample of a compound that contains only hydrogen and sulfur is combusted and yield 10.0 grams of sulfur dioxide and 2.81 grams of water. The molar mass of the compound is 68 grams per mole. What is this compound's molecular formula? Okay, so now we get to sit there and talk about the molar mass of the compound, right? So first off, let's think about, because you guys have already learned how to do chemical equations, kind of think about this in a different way. I'm going to put together a pseudo-chemical equation because we don't know enough about the compound to sit there and give a balanced chemical equation. We know that it's made up of what 2 components?
Hydrogen.
Hydrogen and sulfur.
Hydrogen and sulfur. We don't know how much of each, so we're just going to put an X here for hydrogen, and then for sulfur, we're going to put a Y. And then this is going to give us, well, it's a combustion reaction. Anytime you see the term combustion, you know that it involves oxygen because you can't get fire without oxygen. This fire won't maintain. So you need that oxygen present to keep things burning. And then we're going to end up with H2O plus SO2. Okay, so if you actually thought about it, you'd end up with like X over 2 for this guy and Y for this guy. Okay, so we're going to kind of take advantage of that. So because we know that all of our hydrogen is coming from this compound and all of our sulfur is also coming from the compound. So, but the thing that we do know is we know that that sulfur is in this 10 grams of sulfur dioxide. So we need to figure out how much of that 10 grams is actually sulfur, okay? So I'm going to show you a way of doing that. So we're going to start off with what's given. We're given 10 grams of sulfur dioxide. Now I'm going to ask you a really hard question. And I want you to think about this. You got to think about it real hard. Okay, so if I have 1 mole of sulfur dioxide. Now remember, moles are quantity, okay? Then how many moles of sulfur are in that 1 mole of sulfur dioxide?
Wait, repeat it.
Okay, if I have 1 mole of sulfur dioxide, how many moles of sulfur are in that 1 mole of sulfur dioxide?
1.
That is correct, because the understood number that's here is a 1,
Yeah.
right? So for every 1 mole of this guy, we have 1 mole of that guy. So we can use that to our advantage, right? So we can figure out how many moles of sulfur dioxide we have, and we can use that to calculate the number of moles of sulfur. So how would I calculate the number of moles of sulfur dioxide if I'm given 10.0 grams? What did we do for the other question when we were given grams?
We use the weight.
Yeah, we use,
The molar mass, right? So we need to use the molar mass or the molar weight or the atomic weight to sit there and do that. So what is the molar mass of sulfur dioxide? Sulfur dioxide has how many sulfurs?
1.
Okay. And how much does sulfur weigh?
32.
So 32 times 1 is going to equal 32. And how many oxygens does sulfur dioxide have?
2. Or 16.
Okay, 16 times 2.
32.
So that's 64 grams per mole. And that's going to be my molar mass. Okay, so how am I going to use that?
So put 64 grams per moles on the bottom.
Okay, 64 grams on the bottom. Then that means I put 1 mole on top.
Yeah.
Okay.
Right?
Yep, that's right.
Okay. So
Okay, and you just told me, or someone just told me, that for every 1 mole of sulfur dioxide I have, I have 1 mole of sulfur. And so then I have moles of sulfur, which is what I want. I want that quantity, right? Okay, what did you guys get?
Is it H4S2?
I divided, I got 0.156.
0.156.
yeah, me too.
Okay. Deanna, you're just a little ahead of the game. Slow down. We got to work through that point. You can't give me the answer at the end of the problem. Okay, so then the next part, we're going to do the same thing with the hydrogen, right? So all the hydrogen is coming from water. So what am I going to do next? If I want to calculate the number of moles of hydrogen.
Do the molar mass for the compound.
Okay, so what is the molar mass of water?
18.
Okay, well, 18. So 16 plus 2 grams per mole. So okay, so now I'm going to ask you another question. So if I have 1 mole of water, how many moles of hydrogen will I have?
Two.
That is correct. So we do the math. What do you end up with?
.312.
Okay, so what do I do next?
Is this when you figure out the lowest?
Okay, so who's the lowest?
Oh.
152. So
Oh, Dr. Henry.
Yep.
I forgot to tell you, the 0.152 is supposed to be 0.156.
Oh, now you tell me.
No, I was just too busy with something.
Telenovelas.
Yeah. Yep.
See, I know. Okay, so we divide them both by 0.152. I mean 156.
So that's 1 and 2.
Okay, so we have 1s,
Mhm.
and then we have 2 h's. So then the empirical formula is H2S. Okay, so how would I calculate the molecular formula? So what else did they give us up there?
The molar mass.
The molar mass of the molecular compound, right? So I have the empirical formula. Can I calculate the molar mass of the empirical formula?
Yeah, doing the same thing all over again.
Okay, so I have 1s. How much does S weigh?
32.
32.
Or 2 times 1. I have 2 hydrogens. How much does each of those hydrogen weigh?
1.
equals 2, so that's 34. So we have 68 divided by 34 grams per mole.
Two.
Okay. Okay, so then our answer would be Deanna. What is our answer?
I came up with H4S2, which is A.
That's right. Piece of cake.
Kind of.
Okay. So at this point, you guys are all familiar with chemical reactions. You know how to balance equations. You should be pretty confident in that. Okay. So evidence of a chemical reaction is going to be a color change, formation of a solid, formation of a gas. You're going to either have heat released, or you're going to have or heat absorbed, or you're going to have light emitted. Okay. When you guys broke open the glow stick, what happened? Or when you guys broke the glow stick, what happened?
There was a change of color.
There was a change of color. What happened when you added the baking soda to the vinegar?
Formation of a gas product.
Formation of the gas product. Okay. So those are all examples of chemical reactions, right? And you guys remember chemical reactions versus physical reactions back in the very first chapter. You thought you were going to get rid of it, right?
Mhm.
Okay. So when we have this chemical reaction that's given to us, sodium reacting with water. So we have sodium metal, sodium salt is added to water. A reaction occurs producing hydrogen gas and sulfur hydroxide and heat. So we write chemical equations to sit there and show this reaction. So what would be the chemical equation for this reaction?
Would it be S plus H2O? Or no, never mind.
No, don't, whatever mind. What is the chemical symbol for sodium?
Na.
Na, yes. So Na, and then you said plus
Yeah, plus H2O.
plus H2O. Okay, so that is good, right? So we have our sodium plus H2O, but we also need to give us the state that our sodium is in. Our sodium is it a solid, liquid, or gas?
Sodium is solid.
Okay. And water?
Liquid.
Okay. So we use that S and that L to sit there and determine whether it's a solid, liquid, or gas. And then we make
H plus NaOH
here.
plus sodium hydroxide and
Like
NaOH.
they say, wear free tie-dye shirt, wear tie-dye, you get in free. Today.
What?
The weed thing, bitch, me what?
Oh, they got one today?
Yes. They said wear a tie-dye shirt, you get in free.
Oh, I didn't know there was one today. I thought it was tomorrow.
So did you guys, you got that? If you wear your tie-dye shirt, you get it for free? Okay, so let's talk about that H. What do we know about hydrogen gas? Or hydrogen? when it's by itself. Have no fear of ice cold beer.
A diatomic.
It's a diatomic. You don't want to forget that because forget it, your equation is going to be completely wrong, right? So we know that that's a diatomic. So is it a solid, liquid, or gas?
Gas.
And the sodium hydroxide, it says sodium hydroxide solution. Anytime you see the word solution, that basically means that it has water in it. So it's going to be aqueous. AQ. Per se. Most cases, it'll be water, unless they tell you otherwise. Okay? And then that heat is going to be a certain amount of energy. We'll talk about that later on. Okay? So is it balanced?
No.
Okay, what can I do to balance it? Come on, we've been doing this since the very beginning. It hasn't
Would
changed.
you
What was that?
would you add a 2 on the product side in front of the Na?
Okay,
So that would give you 2 sodium. So then you would add a 2 to the sodium on the reactant side.
okay,
And then if you add, oh shoot. Oh no, yeah. If you add a 2 to the H2O at the reactant side, now it's balanced.
okay. So that's 4 hydrogens, 2 oxygens, 2 oxygens, and 2 sodiums. Good job. That's it. Piece of cake.
Yes.
Okay, so let's make it harder. Okay, so this basically is those symbols that I was telling you about, the S, the L, the T, and the AQ. Aqueous basically means dissolved in water. Do's and don'ts of chemical reactions. We've talked about this. You can't just make stuff up and just throw things in there because things aren't balancing out, right? So you got to have stuff that's going to be really there. You want to make sure that your chemical formula is correct, because if your chemical formula is correct, then you're okay. But if your chemical formula is incorrect, then your balancing out is going to be totally incorrect, okay? So first thing that you always want to do is write down the chemical formulas and make sure that they're on the right side where they're supposed to be. If they're reactants, they're on the reactant side. And if they're products, they're on the product side. Then you want to use the coefficients to balance them out. Okay. Just like you guys did earlier. Okay, so now balance the equation for the reaction of a solid phosphorus pentachloride with liquid water, yielding aqueous solutions of phosphoric acid and hydrochloric acid. What am I going to do? Am I going to sit in the corner and cry?
No.
Yes.
First, we would build the equation, right?
Okay, so what is our equation?
Cl5p. Phosphorus. Yeah.
PCl.
5.
Okay. Solid, liquid, or gas?
Solid.
Solid. That's an S. Okay, plus
H2O.
what are we making? Is that solid, liquid, or gas?
Liquid.
H3PO4. And plus HCl.
Anything that is there anything that I need to put next to them? Let me know what they are.
If they're solid, let's see.
HCl.
It says yields an aqueous solution of phosphoric acid and hydrochloric acid. Is there something I need to put next to them? Let me know that they're acid. What was that?
Aqueous.
H and aqueous.
AQ. That's right. Okay, is it balanced?
No.
No.
Okay, what do I need to do to balance it?
You can put a 5 in front of the hydrochloric acid,
Okay,
and then a 4 in front of the H2O. No, H2O. Yeah.
okay, is it balanced?
No. Oh yeah, it is. It is.
Okay. So we have 3 hydrogens here, 5 hydrogens here. So that's a total of 8. 4 times 2 is 8. We have 4 oxygens here. We have 4 oxygens here. 1 phosphorus, 1 phosphorus. Looks good to me. Piece of cake. Good.
Yeah.
Moving on. So we've talked about what things mean, right? In terms of at the particular level, that means that we have 2 atoms or 2 molecules of hydrogen gas for 1 molecule of oxygen gas. And then that's going to make 2 molecules of water. So when we're talking about the particulate level, we want to make sure that we can't have a half of a molecule, right? So when you're balancing the equation, we want to make sure that it's balanced and you don't have a half of a molecule, right? On the molecular level, technically we could have a half of a molecule or a half of a mole, you know, because it's on a molar level. It's on mass quantity, okay? So do you guys see the difference there? You can't have a half
Yeah.
of the molecule,
Mm-hmm.
where here you can, so.
Okay.
Okay, so that's pretty much it in terms of writing chemical equations. So then we talk about the types of equations. So we kind of talked about this in the lab miles and miles ago, right? We're just kind of getting caught up on the lecture here with it. So we have A plus B is going to yield our synthesis reaction, okay? So when you have 2 things that are coming together, they're synthesizing something. Okay, so write the equation for the combination of aluminum, solid aluminum, and gaseous oxygen to form solid aluminum oxide.
Dr. Henry, you're talking about the lab that was already due?
Yeah, because this is all review. You've done all this stuff before. We've talked about it before. We've been talking about this since the very beginning of class. Right? I'm not
Right.
teaching you anything new.
I was just double checking which lab you're talking about.
So what am I going to do in this case?
So
Start with solid aluminum.
Okay, what does solid aluminum look like? What's the chemical formula for solid aluminum?
Is it 4A?
It's what?
AL.
4AL. Yes, sorry.
You mean AL,
Parentheses S
parentheses S.
plus 3O2.
Oh, you're slow down. We want remember, we want the
O2.
we want the reactants first before we make sure that they're right. So we want O2. Okay.
Yields AlO3.
Is that right?
Or Al2, sorry.
That's right. Al2.
Sorry.
Solid, liquid, or gas?
Solid.
Oh, solid. I'm sorry.
And we know that this was a gas. Okay. Is it balanced?
No.
Okay, what do I need to do to balance it? Okay, now you can tell me the answers.
Put a 2 in front of Al.
A 2 in front of Al. Okay.
And then we have 2 and 2. And then we have 3 oxygens on that side. So we only have 2 on this side. So put a 1 in front of the O.
Which O?
That one.
Okay, is that balanced?
No.
Oh, put
Okay.
it.
No, put a 3 in front of the O2.
Put a 3 in front of the O2. Okay.
Oh, yeah.
Put 4 in front of Al and then H2 in front of Al2O3.
Okay. I heard 4 in front of the Al
Yeah,
and then a 2.
yeah.
Okay. Now is that balanced?
Yeah.
Yeah.
Okay.
Yes.
Okay, we want to remember it's multiplication, not addition, right? So coefficients is multiplying it by that number. Okay, piece of cake, not too hard, not too shabby.
Not bad.
Okay. So we have what we call a decomposition reaction. Decomposition, breaking down. So in this case, you have AX, and you're breaking it down to A plus X. What are we doing today in lab? Okay, so in this case, I'll give you an example. Water decomposes into elements of, water decomposes into its elements when electric energy is added. Write the equation. So
would it be H2O yields H2O2?
is that what you're saying?
I mean, H2 plus O2.
Okay.
I think it. I don't say it.
Okay, is it balanced?
No.
What are the states? We have water.
Oh, yeah. Yeah.
Okay, so what do I need to do to balance?
Put a 2 in front of H2O. Oh, wait. Yeah, 2, and then put a 2 in front of H2.
Okay, piece of cake.
Yeah.
Okay, so some reactions are reversible, meaning that they can go back the other direction. And when they are reversible, we'll indicate it by having arrows going in both directions. Often when things go into equilibrium, that also is a sign of reactions that are able to go in both directions concurrently, right? So they reach a point of equilibrium. So you have both states or both things happening at the same time, okay, in that particular environment. We'll talk a little bit about that, hopefully. The other one is called the single replacement reaction. These reactions are they're often redox reactions or oxidation reduction reactions. They're called oxidation reduction reactions because in those cases you have electrons being exchanged. And I'll show you an example of that here in a second. Okay, so in the case of a replacement reaction, you're replacing B with A. So all you're doing on the other side of the reaction is replacing B with A. So I kind of like thinking of it as you're replacing the old girlfriend with the new girlfriend. Okay, so now when you're doing these replacement reactions, the elements have to be kind of alike, right? So for instance, if you have a metal, you can replace it with another metal, or you can replace it with hydrogen, okay? But when you have a non-metal, you can only replace it with another non-metal, okay?
So what you're saying is one of the elements have a type?
Exactly. Exactly. Okay, so copper reacts with a solution of silver nitrate, right? The chemical reaction. So what are my reactants?
Copper and silver nitrate?
Okay, so give me the chemical formula for copper.
Cu?
Solid, liquid, or gas?
Solid.
And the chemical formula for nitrate or silver nitrate?
AgNO3.
Solid, liquid, or gas, or aqueous? Solid, liquid, or gas, or aqueous?
So, liquid.
Nope.
AQ.
AQ.
AQ. Remember, anytime you see a solution, think AQ. Okay, so what's happening? What are going to be the products? What are going to be the products?
Would it be silver by itself and then copper nitrate, or?
Silver by itself. And copper nitrate. Copper what nitrate? I should tell you this. So usually when you have a replacement reaction or an oxidation reaction, most metals that are transitional metals, they like 2. So they like to be 2+. Except for silver. Silver is always going to be that +1. So it's going to be copper 2 nitrate. So how many nitrates do I need to count?
Can you repeat that? You cut off a little bit.
I said, sorry. It's going to be copper 2. So how many nitrates will I need to balance it out?
2.
2. Okay. Is it balanced?
No.
No.
Okay, what do I need to do to balance it?
Put a
Add
two
a
in front
two
of
and
Go ahead.
So- I heard
add a
put
two there.
Yeah.
Add a two, yeah.
Okay, and
There.
here. Okay, piece of cake.
Yeah.
Okay, our next type of reaction is called a double replacement reaction. So in this case, you're switching out partners. So A is going to go with Y, and B is going to go with X. Okay, so often this will be a precipitation reaction. This is also called a double replacement reaction or a double displacement reaction. Okay, I like to call it a swingers reaction. Okay, so we have silver chloride precipitates when solutions of sodium chloride and silver nitrate are combined. Write the chemical equation for the reaction. What am I going to do? What are my reactants? What are my products?
Silver chloride is one of your reactants.
Is it one of my reactants? Let me reread the question for you. It says silver
Oh.
chloride precipitates.
Sodium chloride and silver nitrate.
Okay, so we have sodium chloride and silver nitrate are going to be my reactant. So anytime you see the word precipitate basically means they come together to form a solid. Okay, so they're coming together to form a solid. So we have sodium. What is the chemical formula for sodium chloride? Sodium chloride.
NaCl2.
The two?
NaCl.
NaC. Okay, is it NaCl2 or is it NaCl?
NaCl2. Isn't chloride a dominant?
It's just NaCl.
NaCl.
Like the
Diatomic is
polyphenol C.
only diatomic when they're by themselves.
Oh,
So when it's oxygen by itself, it's going to be diatomic. Cl is only going to be diatomic when it's by itself. Okay. Okay, and this was solid, liquid, gas, or aqueous.
Aqueous.
And silver nitrate.
AgNO3.
Solid, liquid, gas, or aqueous.
Aqueous.
And it's going to yield
Silver chloride.
Aqueous. Yeah. Are you freezing or am I freezing on my end?
Are you talking to me?
Yeah, I can't tell. There's like a lag.
I don't know.
I know. It'd help if somebody else mentioned if you're lagging on their screen too, or
Nah, Dr. Henry's not lagging.
okay.
I think
my
it might be
screen.
yours because you
Yeah.
can barely hear you.
Okay. Thanks, guys.
Okay, is silver chloride solid, liquid, or gas, or aqueous?
Aqueous.
That word precipitate means what again?
Come together.
Forms a solid.
It comes together to form a solid. So is it going to be solid, liquid, gas, or aqueous?
Solid.
Solid.
Okay.
Okay, and then what is going to be the other product?
Sodium nitrate.
Sodium nitrate. That is correct. And that one is going to be aqueous because they didn't talk about it. That basically means it's hidden solution. Piece of cake. Is it balanced?
Yeah.
Good job. Okay, the next type of reaction is basically, it's the same thing as the double replacement reaction, but it's a special double replacement reaction. This is called the acid-base reaction. You get an acid, you get a base, you usually get water and a salt, okay? So, and that's when the acid is being defined as the hydronium ion donor, or H+ donor, or proton donor. And the base is being defined as a component that has hydroxide, okay? So like, for instance, we'll have sodium hydroxide and hydrochloric acid, okay? And then as a result of that, we'd get water and sodium chloride. Let me write that down. So
what's a good analogy for this one?
still a double replacement reaction, it's still a swing reaction. Just a special case. So this could either be a solid or it could be aqueous. And you end up with water. And salt. Okay, you guys see that? Because all this is you'll say this guy is gonna go with this guy. And then this guy is gonna go with this guy. So in this case, we'll have these two coming together, then we'll have these two coming together. So we get HOH, which is just H2O. Okay, you guys see that? Yes, no, maybe?
Yes.
Okay. Let's move forward. HOH is the same thing as water, H2O. Okay, write the equation for the reaction between sulfuric acid and solid aluminum hydroxide.
So H2SO4.
And we know that all acids are,
Aqueous.
okay. Plus,
AL parentheses OH parentheses 3.
Solid.
then we're gonna make
Water.
and
H2O.
what else?
Al2 parentheses SO4 parentheses 3.
Okay, is it balanced?
No.
Okay, what do I need to do to balance it out?
put a 2 in front of the AL. OH3. And then put a 3 in front of the H2SO4. And then put
Okay.
a 6 on H2O.
Okay, let's see. That's 6, that's 6, that's 12, that's 6, and that's 12, so that's 6 and 12. Okay, looks good. Piece of cake?
Yeah.
Okay. These are all the different reactions that we've talked about. Piece of cake?
Yeah.
It's all chapter 8.